Hello everybody, let us see magnetic boundary conditions. In this magnetic boundary conditions means the behavioral of magnetic field and magnetic flux at the boundary between two different magnetic media. So we make use of Gauss law for magnetic field is circular integral B ds equal to 0, Ampere's circuit law integral H dl equal to I. So consider the boundary between two isotropic homogeneous linear materials with permeabilities mu1 and mu0. At the boundary, the magnetic flux density B may be decomposed into a normal component Bn at a tangential component Bt. Applying Gauss law for magnetic field in a small pillbox shaped volume. So Ht1 plus Ht2 is a tangential component of H on the boundary of two differential media. Hn1 plus Hn2 normal component of electric field. Normal component of B is continuous across the boundary between the two adjacent media. If the both media across the boundary are not conductors, H12 equal to Ht1. The tangential component H vector is continuous across the boundary between the two adjacent media. The figure are mentioned here. For the analysis of tangential component, a closed path is constructed across the boundary above. By Ampere's law, circular integral HTL equal to I enclosed. That law represented and derived from various medium stages. That medium stages are noted down this graphical representation. So equation 1 and 2 can have to summarized and come out those two equation into third equation Bt1 by mu1 Bn1 equal to Bt2 mu2 Bn2. So B1 sin theta 1 by mu1 B1 cos theta 1 equal to B2 sin theta 2 mu2 B2 cos theta 2. So the sin by cos takes to tan. So tan theta 1 by mu1 equal to tan theta 2 by mu2. So we can get tan theta 1 by tan theta 2 equal to mu1 by mu2. Let's discuss about what is inductor, how the inductance to be working across this function. So let us see what is inductor. If a time varying current flowing through a coil, there is an EMF induced in it. The induced EMF across the coil is directly proportional to the rate of change of current with respect to time. Due to the property inducing EMF, all types of electrical coil can be referred as inductor. So an inductor is an energy storage device which stores energy in form of magnetic field. Then we know what is an inductance. The induced EMF across a coil is directly proportional to the rate of change of current through it. The proportionality constant in the relation is known as inductance. So we can get V proportional to di by dt equal to V equal to L into di by dt. So we can get L equal to V by di by dt. Next we have to see inductance of a solenoid. A solenoid is a long thin coil. Example, coil whose length is much greater than its diameter. B is given by B equal to mu naught Ni by L. So the total magnetic flux through the coil is obtained by pi equal to mu naught Nia by L. But inductance is given by L equal to N by I. It follows that the inductance of a solenoid is given by L equal to mu naught N square A by L. Next, energy stored in inductance. The work done per unit charge and the charges passing the inductor is E. The current I is the charge per unit time passing through the inductor. The rate of work done by the charges against the EMF. That is the rate of changes of energy of the current is given by dW by dt equal to L into di by dt into I. So Li di by dt. We can get dW equal to Li di from above equation. So this equation can concluded by using the differential into integration. W equal to integral of 0 to I naught L into I di. So we can get W equal to L into integration of 0 to I naught I into di. Finally, the conclude of energy stored in inductance W equal to half L I naught square. Next we have to see energy density. The energy density says consider an ideal solenoid. The inductance of a solenoid is given by L equal to mu naught n square A by L. So it reduced W equal to B square to mu naught L A. So the magnetic energy density inside the solenoid is W equal to B square by 2 mu naught. Thank you.